Remember, second semester, it's all these kind of little specified chapters. Like last chapter was polar coordinates. This one we're going to talk about vectors. The next one we get into like matrices. Then we're going to get into sequences. It's all these little specific topics we're going to work on today. So we're going to talk about what is a vector, how to graph a vector, anything and everything you could ever imagine with a vector pretty much. So just for fun, little reading, why is vectors important, you know. So in applications of mathematics, certain quantities are determined completely by their magnitude. You're going to see magnitude today. We're going to calculate that. That, of course, is the length, mass, area, temperature, energy. I feel like I'm teaching physics, to be honest, today. We speak of a length of 5 meters or a mass of 3 kilograms. Only one number is needed to describe the quantities. We call it a scalar. On the other hand, to describe the displacement of an object, 2 numbers are required, and this is what we're going to have today. We're going to give the magnitude, the length, and then the direction. So it almost kind of makes me think of polar coordinates again. You're going to have like the r theta, the length, and the direction. We're going to use an angle for that. So to describe velocity of a moving object, we specify both the speed and direction of travel. You can see they talk about velocity, acceleration, force, all that sort of good stuff. So we're going to use vectors for all of this fun-filled physics knowledge. So let's get into what a vector is. So a vector in the plane is a line segment with an assigned direction. And of course direction, I mean even slope, up and over. I mean everything has a direction when we talk about the graph grid. Now to draw your vector or to sketch your vector, notice you have a point, a dot, and an arrow. A, of course, that is your starting point, obviously. We give that a fancy name, your starting point, so we call it the initial point. And B, of course, where we end up, our final, our terminal point. And to name a vector, okay, the order is important on how you name a vector. Vector AB is different than vector BA. You can't just interchange them. You have to start at the initial point and go to the terminal point and then use a little vector symbol above it. That is not the same as vector BA. They are not interchangeable, just for the record. Now, some vocab, of course. We're going to be calculating magnitude today. That is the length of the segment. And just like everything, we're going to be talking about how far over we go, how far up we go. It's really going to look Pythagorean theorem-ish to us again today, okay? And to do the magnitude, it looks like absolute value, but it really, in the vector world, this means magnitude. So the vertical bars are asking you for the length, and not the absolute value in the vector world. Now, you'll see too, it's really fun for me to type it all. When we do vectors, of course, they can use some bold-faced letters to represent them, one of the notations. So you can do it vector AB, or they might just define it vector U. Different ways to do it. And of course, two vectors are considered equal if they have the same direction, so they're headed the same way, and the same length or magnitude. So of course, the first section usually of every new chapter is kind of a big one because we have all this preliminary like vocabulary, how to set up everything. Everybody got everything filled in? Okay. So adding two vectors, let's talk about that. You can see some pictures down there. Nothing for you to fill in, just some pictures to look at. I wish we had color copy machine too, so mine are in red here. To find the sum of any two vectors, we sketch vectors equal to A and B, same initial point, starting point. And of course, you're taking a look at this first picture here, the terminal point of the other. So if you draw, of course, your vector AB, BC, you can see it's the red one. Here you draw your vector U, then you add on B, the diagonal there, the red one, ends up being the sum. So drawing the sum is going to be easy. It involves, I know you're shocked by this, addition today. Okay, so flip the page. Page 2 of, if they're single counted, was it 1, 2, 3? Oh yeah, okay, good stuff. Let's just keep going. So you can also multiply vectors by a scalar. Now this is nitpicky stuff, people. Notice the C is not bold, okay? That is important. The vector is the bold letter V. The C, not being bold, is your scalar, what you would multiply to the vector. So just take a look at that. And of course your magnitude, absolute value means magnitude or the length. So when you multiply by a scalar, it has the same direction. If you multiply it by something like, let's say multiply it by 2 or whatever, it's going to have the same direction as long as your scalar is positive. If your scalar is negative, it's going to affect the direction. And we're going to look at these pictures down here. So it's going to go opposite. So if you look at your original, mine's in red here, red vector, if you multiply it, like I said here, 2, clearly it's double the length, it's headed the same direction. But if you do negative 2, it goes in the opposite direction. Obviously a half as much. Negative a half would be half as much, but the opposite direction. Easy enough. Shocker, if you multiply by 0, you get the 0 vector. So that's really worth writing down. Multiplying by a vector, of course, has the effect of either, as you can see, like the 2, the double, stretching it. Or, of course, half as much, or like this little guy, a third as much, shrinking. And again, it's going to be easy for us to do. We're just going to multiply by whatever value they want, and it's going to be easy to see. But clearly double the length, half as much, and obviously a negative is going to be opposite direction. Okay, difference of a vector. Now remember, difference is the same as adding a negative. So really, again, I wish we had color copy machines. My blue U and V one, so you can see they did the sum, but of course the difference, adding -1 times it, goes in the opposite direction. -1 times V. That's what they really are showing you there. But again, don't get too carried with all the pictures, because when we start actually having real numbers in here and you do the multiplication, all of that will calculate out easy for you. Okay, so how to draw a vector, name a vector, all this sort of good stuff. So, nothing for you to write down, just take a look at it. Oh boy, just take a look at it. So, describing it using component. We need to talk about this vector component form. Boy, that's a mouthful. So, it shows you how to do the vector FG. So, when you name your vector or do your component form here, it's kind of opposite of slope. You're going to go across first, count how many across, and then vertical. And notice, it's teeny tiny, how to do your vector component form. You're going to see that notation a lot. Notice, my artistic skills here, they're not parentheses. They're kind of pointed on the ends. That is your vector component form. So when I look at this, it's not an ordered pair, it is a direction. This is saying, hey, you got to go right 5 and up 3. Directions, not points, not ordered pairs. So just take note of that. Man, we are cruising through page 2 almost. Maybe. Page 2 of 7. Okay, find the component form of the vector with that initial point and the terminal point. So component form, and kick it off there, kick it off. It's at the very bottom of page 2 there, that example one's still on there. Now, all you have to do is a little mental math here, people. Remember, we want the horizontal distance first. So from -2 to 3, you went 5, right? And then you're going to do the same for y. From 5 to 7, you went 2. There it is, your vector component form. So that's saying you moved this point right 5 up 2. That's, yeah, the math is easy. It's just a lot of notation to get through. And just like that, we're on page 3, everybody. Okay, if the vector, notice vector form, is sketched with that initial point, what's the terminal point? So you are moving this point according to the vector. The vector is telling you right 3, up 7. So if I want to make this right 3, up 7, where would you end up? 5'11". Right 3. Okay. That's all it is. Then that's as wild. Well, the word problems at the end get a little, but the rest of it, very, very simple today. Very simple. All right, let's graph. So sketch representation of vector. 2, 3 with those points. Okay, power the smartboard. I'm going to do it different colors. They just have different ones here. I'm going to start at 0, 0 for the green. Now, there's my initial point. They want you to apply the vector 2, 3. So 2 would be 2 right, 3 up. Right? 3 up. So there is my first vector. I'll do them all in different colors, and I'm going to do this one in blue. So I'm going to start at 2, 2. There's my initial point. Apply your vector, right 2, up 3. Pretty exciting stuff. All right, I'm going to do this one in red. Initial point, -2, -1. Apply your vector, right 2, up 3. And our last one, we'll do this one in black. Initial point, 1, 4. And then your vector, right 2, up 3. So that's all it takes to graph vectors on the coordinate plane. Any questions on that? All right. Too easy, I know. So I kind of talked about this being Pythagorean theorem-ish, of course, when we talked about the magnitude, okay? So take a look, magnitude of a vector. So when we take a look at this, this is pretty simple. So our red vector, of course, if you think about drawing yourself a right triangle and you're doing Pythagorean theorem, a1 squared plus a2 squared equals c squared, the hypotenuse squared, and then you would root it. So when in doubt, if you're like, oh my gosh, I don't remember how to do it, Pythagorean theorem. Make yourself your right triangle, use your Pythagorean theorem. So this is one I don't really get carried away on the formula with it, because I'm like, well, we can just do a triangle and do Pythagorean theorem. So here we go. Find the magnitude of each vector. So you can go straight off the formula, or of course, draw the picture. Let's just do the formula. So the magnitude of u, so we're doing our Pythagorean theorem, we would square root our answer. We got to square both of these values, of course. Probably can do that a little mental math. 4 plus 9. And of course, if I could, I would try to simplify that, but 13's prime, so I'm not. We always simplify in here. Unwritten rule, we always simplify. Okay, 5 squared, 0 squared. I don't even know really why I'm writing 0 squared. That seems pointless. Square root of, okay, 5. And, oh, good, some fractions. 3/5 squared plus 4/5 squared. Now, okay, let's, I can't help myself. So tests, like I said, really, really good. Just a couple of us are going to be mad because this is like one of those minus half things. When you square a fraction, I had people squaring just the top and not the bottom. We got to square both, just for the record.
Oh, did you do that? No, I didn't.
Okay, so add those together. 9 25ths, 16 25ths, 25th 25ths.
1.
Final answer.
1.
Thank you. Do you know how many times I see people leave the square root of 1 and I'm just like, seriously?
Did you put simplify?
Seriously? Seriously. Okay, any questions on that? Man, we are cruising. Okay, this is easy. Algebraic operations. So this is all on your sheet. There's nothing for you to write down. Again, I'm looking at this. It's common sense to me. If you want to add two vectors together, you're going to add the first values and then the second. If you're going to subtract them, you're going to subtract the first values and then the second. If you're multiplying by a scalar, you multiply everything on your vector component form by that scalar. Next page. Look at us go, class. Look at us go. We might get it all done.
I hope not.
Yeah. Man. All right, here we go. Find u plus v, u minus v, 2u. Well, we do have a lot to calculate. We probably should go slow, right?
Yeah.
Okay, component form. Super easy. I'm going to do the horizontal part. The first value is -2 plus -1, of course. And then 3 plus 2. I'm hoping we don't need work for that. U minus v. Okay, so -2, careful on your signs. What's -2 minus -1? -2 minus -1. Got it. 3 minus 2. All right. 2u. So here's your first scalar. So of course we're just going to multiply everything in u by 2. So negative 4, 6. And what do we got next? Negative 3 times v. Now, of course, be conscientious. Make sure you're doing it to v, not u. So v, negative 3 times negative 1. And just remember, if you were graphing it, if you multiply by a negative, it would be going the opposite direction as our original vector. Just thought I'd point that out, of course. Okay, what else we got? Oh boy, 2u plus 3v. Again, you can still do that all mental math style. If I do 2u, negative 4, 3v, negative 3, add those together. Then do your 3v. What's your last number?
12.
Got it. Okay. I don't need any work for those. You can just simply do the little calculations in your head. See, we're going so fast. It's so great. Okay. This again, kind of common sense stuff. Vector addition. It doesn't matter what order you add your vectors in. If they tell you plus v and you decide you want to switch it up and do v plus u, you'll get the same thing. Doesn't matter. Order you add in basically does not matter. We know that. 2 plus 3, 3 plus 2, it doesn't matter. U plus the opposite will get 0. We know that, okay? To do your length, your magnitude, if you have a scalar, you have a choice in how you can calculate that. You could do the scalar to the vector first, like how we did 2u and negative 3v, and then do the magnitude, do the Pythagorean theorem part of it. Or you could do the Pythagorean theorem of each of them separate and then multiply it at the end. I find that a little obnoxious. I just multiply first and then do the Pythagorean theorem. All right, of course you can distribute a scalar through. 1 times the vector is the vector, 0 times the vector. Okay, we got it. Okay. Vector of length 1, of course, has a little fancy name. We call it the unit vector. So you're going to see we're going to start using I and j. So I, of course, represents the horizontal. 1 is in your horizontal location. J is your unit vector, of course, for your vertical location. So the next thing I'm going to show you. So you can take a vector and, of course, rewrite it with our I and j, meaning just something easy. Like if I gave you the vector 2, 3, that's the same as 2i, 3j. It's just a different way to write the exact same thing. And you just, this is one of those things you just have to read closely. Because they might say, hey, express your vector in terms of I and j. So you want to give the 2i, 3j. Or they might just say component form, 2, 3. Just read close, right? Okay, write the vector in terms of I and j. That should be simple. We just did that. So it's going to be your 5i. I'm not writing plus negative 8.
Why do we have this when you're using those formulas?
Say it again. What, Avery?
Nothing.
I just didn't hear you. No, I just didn't hear you. I didn't want to ignore you.
No.
Why do we have to do this? Why are we doing it? Just to make your life more complicated. Just another way to represent vectors. Okay, if you write 2u plus 5 in terms of I and j. Okay, so you're doing the same process. 2u, so I'm going to do a little work on this one. So if I do 2u first, I'm just going to double these. I'm going to do 5v. So run a 5 through the v. And again, some of you can mental math this. I'm well aware. 5 times 6, 30. And then, of course, it wants you to add those together. All right, we'll add them together. Do the i's together. So that's going to be a 1i. I'm just going to put I. 4 plus 30, 34. We're getting close, kids. We're getting close.
We don't like
We just take like a brain break. I mean, I am old and slow. It will take me a few minutes to pass out all the tests and stuff.
Exactly. When you want to.
Okay, so horizontal, vertical components. Okay. Let's get through example 5, and this is going to take a tick to talk about, okay? It's easy, I promise. Oh, Lord. So, let V be a vector in the plane, focus here, people, initial point at the origin. So this is why we always, of course, do polar coordinates first. The direction of V is theta, the smallest positive angle in standard position. So, just like when we were doing our polar coordinates, our x coordinate you have to do cosine. Cosine's our horizontal distance, sine, of course, the vertical distance. So it's kind of the same idea as what you were using on your polar coordinates. So when we look at this craziness, let V be a vector magnitude and direction theta. So if you want to, of course, come up with your values, you can do the magnitude times cosine of theta for the horizontal, magnitude times sine of theta for the vertical. So this is why I said you might want your unit circle out, because we're going to have some angles here. We're going to have to take a look and get the sine and cos. Do you need a sec to get your unit circles out?
No.
Okay. Just a thought I'd ask. Now, let's say we're on a quiz, we're on a test, we're like, holy cow, I totally forgot this, right? We should be able to think our way through it. Vector has a length of 8, direction of pi over 3. So let's say I totally blanked, because of course math, pattern, common sense, we got it. So I'm thinking to myself, okay, pi over 3. How many degrees is pi over 3? 60. So I'm thinking about, 60 degrees. I'm not going to get my protractor out and measure. I'm just going to kind of ballpark it. 60 degrees, or pi over 3. And our magnitude, 8. So of course, 8 is the length of the vector. So they are asking you for the horizontal and the vertical. Well, we can do this pretty easily, of course, with our unit circle. In worst case, you could use SOHCAHTOA to find the sides, but that seems like a whole lot of extra work. Or even, 60, this one, I'm doing 30, 60, 90s in geometry if we had to. But for us, super easy. We're going to do our length for the horizontal times the cosine of it. That's going to give me the horizontal. I'm going to calculate that in a second. And then the vertical would be the length times the sine.
Oh, we're just doing that.
Just how you were kind of doing your polar coordinates. It all is related. So look on your unit circle, or maybe you just know it.
Yeah.
What's the cosine of 60? Cos of 60 is a half, yep. So we're going to have 4. Sine, what's the sine of 60? We're at 3 over 2. Good mathematicians that we are, we're going to reduce 8 over 2 down, right?
No.
Yeah. Okay. Now, notation, reading, you know the drill. If we were asked for vector component form, I would just throw this down. But it wants it in terms of I and j. Okay, fine. So I'll put 4i plus 4 square roots of 3j. And that's how we're doing it. And of course you'll be provided or get to use your unit circle too on that. So you don't have to worry about trying to redraw and memorize all that stuff. That is just time consuming. All right, let's do B. Find the direction. So the angle, direction, theta, angle, direction of that vector. Okay, so let's say we're like, oh man. So this is just me. A lot of times you'll see, just because, I don't know, this is how my mind works. I like my vectors in the component form. I just like to work with the numbers. So I'm looking at that and I'm like, okay, so that is telling me negative root 3 is to the left and you're going to go 1 up. So I'm going to make myself a little triangle out of that. Negative root 3, I'm just ballparking it, 1 up.
Yeah, it's not. It's not great.
Now, we could find the hypotenuse if we really wanted to, or really, we should just know it. What's the hypotenuse? 2, because we're on one of our special triangles. So for funzo, what's this angle?
150.
Well, give me just the angle in the triangle for right now. 30. Opposite one is the 30. But remember, of course, we are going to measure from 0 around. So we really covered how many degrees? 150. And they magically just randomly think you're going to know they want that in radians. What is it in radians?
No clue.
Pi over 6.
Good work.
Thanks.
Proud of you, Anna. Now, the other way too, you could have done it too, if you're like, oh, I hate drawing that graph, it's so obnoxious, okay? You could have thought to yourself, because remember, I'm just crossing the 2 off, I'm just looking at my given information. Oh, well, you could have done like tangent inverse on your calculator. Opposite adjacent. That would also give you the 30 degrees. It's up to you, but you have to recognize you're in quadrant 2, so make sure this will give you the 30 degrees. You're going to have to recognize due to location it's really 150 when you measure from 0. So just be conscientious of that. Are we